hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Now, in this specific discussion, we're going to look at the Gibbs Helmholtz equation. And of course, this is going to be giving us the relationship that's applicable to any chemical or physical change. And of course, we had said that from the second law of thermodynamics, we can be able to describe the concept of equilibrium and spontaneity. And of course, we can be able to obtain other results which are going to be valuable for us. Now, the Gibbs Helmholtz equation is going to give this specific, aspect, whereby we are going to see that we can be able to derive other aspects like enthalpy of a reaction from the knowledge of the free energies that are being described by this specific equation of a Gibbs Helmholtz equation. Now, this is going to be under the aspect of a constant temperature and pressure. And of course, we can be able to describe this specific aspect by considering the two states of energy of a system, whereby we can be able to say let G1 be the free energy of our system in its initial state at a particular temperature. And of course, we're going to describe the value of this specific system for the particular, of course, initial state, as I've said, at a particular temperature. Now, this temperature can be represented in form of a T, and of course, we can be able to give the values of these two states using a particular variable. So, in this case, if G is representing the energy state of that specific system, at a particular temperature or the change at a particular state, initial state, we can be able to give G in terms of a G1 and temperature in terms of a T1. So these two specific states can be described in terms of an appreciable amount in either temperature or this particular form of energy. Therefore, we're going to have this energy given in terms of a G1 plus D G1 given as that. So this is going to be an infinitesimal, perhaps, or an appreciable amount of change in energy of this specific system. And for the sake of, for the case of temperature, we can be able to give the change in temperature in terms of course, T1 plus D T1. And of course, those are the various changes that we can be able to give this specific state. So with this particular, of course, a description, we can be able to describe as, of course, an T2, therefore, which is going to have an implication. Going to describe the states of this particular equation for G2 plus DG2, and the second state for a temperature is going to be described as T2 plus DT2 given as such. So using these two specific equations, we can be able to find the difference in those two specific states from the general representation of the Gibbs free energy equation we had used in our first discussion on this specific aspect as delta G. So generally, we are given delta G in form of VdP minus SdT given as such. So this was a general representation of course, the Gibbs free energy, of course, of a particular description under constant, of course, of volume and entropy. And we're going to see that there's going to be variation of pressure and temperature in this particular case. So therefore, from this, we can be able to take note of some changes which are going to be taking place between G1 and G2. So therefore, we can be able to describe under constant condition of pressure, we can be, or pressure or temperature, we can be able to describe a version of this specific Gibbs free energy that we have given for G1 and G2 respectively. So from this specific equation, if we have a constant pressure, we will be having the dP, or the change in pressure, equivalent to 0. Therefore, this equation will be given in form of a negative SdT given as such. So therefore, for the first or the initial state of this specific energy, this is going to be given as G1, and then we're going to have S1 given as such. So this is going to be S1 G1 given as that, and then under the same condition of constant pressure, we're going to describe the second state of this energy as S2 D2 given in that specific order. Therefore, from these two states, we can be able to describe the relationship between the first and the second state of this energy using the general equation of d g2 minus g1 given as negative s2 minus s1 dt using that specific relationship. Therefore, this is going to give us a general implication of this particular equation as a delta G, which is the change in Gibbs energy, minus delta S, of course, and this is going to be dt given as such. So this, of course, is going to be a relationship that is going to be given by the change in entropy and Gibbs energy. Now we can be able to make delta S a subject of this formula by dividing it with that specific ratio. And this is going to give us the equation of the form d delta G over dt, which is going to be negative delta S. Now we had looked at our first equation from this specific case under constant temperature, and of course it had given us the specific, of course, general equation for this, which we said was delta G given us change in enthalpy T delta S. So this was our discussion on the, of course, free energy and the equilibrium. I'm going to put a link of that specific video in the description box of our discussion of this particular video. So in this case, of course, from this function of the equation from the equilibrium free energy, we can be able to do a substitution for entropy and find another function of the equation that is going to give us a general relationship between this entropy and the Gibbs free energy. So we're going to have this one given as delta G is equivalent to delta H. And this is going to be negative this value. So for us to find this one, we're going to have it as a plus d delta G over dt given as this. And this is going to be under the condition of, as I mentioned, constant pressure. This is going to be given as this. So this is going to be under constant pressure given as this. So the resulting equation from this is going to be giving a function of what we refer to as Gibbs Helmholtz equation. And this particular equation is going to be useful, as we said from our first case, since it's going to display the aspect of an equation that is giving the relationship between, or giving the relationship that can be applicable for any physical or chemical change. And of course, from this specific equation, we can be able to, of course, evaluate or calculate the various values for enthalpy reactions of various reactions. Having had knowledge of those, the free energy of those specific, of course, changes, then therefore we can be able to calculate the concept of enthalpy change. And this is going to be under the conditions of constant temperature or pressure, which we had, of course, considered in our first case in order to find the change in energy, which I've described above. So this is going to be the final, of course, a representation of this particular Gibbs Helmholtz equation. And as such said, it's going to be more convenient for us in trying to describe these various physical and chemical changes of various, of course, states and equations. So that is it for now, guys. Kindly check our description boxes for various links of other videos which are going to be applicable and, of course, assisting us understand these particular topics and details. So that is it for now, guys. Bye, God bless you. Catch us in our next video.